Okay, this is going to be a quick video because the purpose of this video is just going to be to go over higher order derivatives. Higher order derivatives relate to both displacement, velocity, and acceleration, but for now we're just going to focus on the act of taking a higher order derivative. So we'll start with example 1 right here, and you can read this preamble here on your own later, but effectively this first example is just asking us to determine an expression for the rate of change of volume of a sphere with respect to its radius, then evaluate that rate of change at a radius of 2 centimeters. So let's find the volume function. Volume as a function of radius is equal to 4 over 3 pi r cubed. Okay, that's just the volume function of a radius, volume function of a sphere. And we can see that the volume is dependent on the input for radius. All right, so let's take the derivative, the first derivative, dv dr is equal to 4 over 3. I bring the 3 down, pi r squared, and that cleans up to dv dr is equal to 4 pi r squared. The example asks us to evaluate the rate of change of the radius at 2 centimeters. So dv dr at when r is equal to 2 centimeters is equal to 4 pi, and then I'll say 2 squared right there. 2 squared, so that's equal to 16 pi. Well, what are we saying here? Okay, so what we're saying is that when the radius is equal to 2 centimeters, the volume is changing at a rate of 16 pi cubic centimeters per centimeter of radius. Okay, so that's the rate of change of the volume with respect to the radius, and that's evaluated right when the radius is equal to 2. Okay, so we're going to start now looking at higher order derivatives, and higher order derivatives are essentially just like taking the derivative of the derivative, right? So for example, if this is a rate of change, then the second order derivative is simply the rate of change, and so on and so forth. So let's start with this first example here. If I want to find the second derivative of this function, then I first need to find the first derivative. So the first derivative, I'm going to use my chain rule. That's going to be 2x cubed minus 5x, close my brackets, 6x squared minus 5. That's the first derivative. The second derivative is the derivative of that derivative. So here, I'll move this over a little bit because I think I'm going to need a little bit more room. Okay, so I'll keep the 2 on the outside, and I'll take the derivative of these two functions right here. Okay, so let's do the, I'll do the derivative of, we'll say the derivative of this one right here. So the derivative of this one is going to be 6x squared minus 5. So the derivative of the first times the second right here. And this is going to be 6x squared minus 5. Then plus the first one, so 2x cubed minus 5x, times the derivative of the second, which is 12x. Okay. So now that I have the second derivative, I'm not going to bother cleaning it up at all, because effectively they just want me to evaluate the second derivative at -2. So I can just insert my -2 into the values of x, and by doing so you'll end up with 10 as your final answer. Okay, looking at this next one over here, it's asking me to find the second derivative of this function right here and evaluate it when x is equal to 2. All right, so let's find the first derivative, so dy dx. And to find the first derivative, I'm going to use the quotient rule. So I'm going to say 1 plus x, so the denominator function times the derivative of the numerator. Derivative of the numerator is 1, minus the derivative of the denominator, that's just 1, times the numerator function, which is just x, all over the denominator function squared, so 1 plus x all squared. So the first derivative is given to me as dy dx. If I clean this all up, I should have 1 plus x minus x all over 1 plus x squared. So dy dx, oops, I've put the square in the wrong place, 1 second. Right there, dy dx is equal to 1 over 1 plus x squared. All right, now if I want to find the second order derivative, okay, I'm going to say d squared y all over dx squared, and now I'm going to take the derivative of this right here. So the denominator function plus the derivative of the numerator function, well, that happens to be 0, minus the derivative of the denominator function. The derivative of the denominator function is equal to 2 and then 1 plus x times the derivative of the inside, which is just 1, and then times the numerator function, that's 1, all over this raised further to the power of 2. Cleaning this all up, I get right here negative 2 minus 2x, negative 2 minus 2x all over 1 plus x to the power of 4. Okay, I can make my life a little easier by doing this. D squared y over dx squared, factoring out a negative 2, 1 plus x, and then I get 1 plus x all raised to the power of 4, and then I can cancel this out right here, and cancel that, and that goes down to 3. All right, now it's just a matter of subbing in x is equal to 2, and if I sub in x is equal to 2, you'll just get, let me just find some space to do this. Okay, getting a little tight here, but d squared y over dx squared when x is equal to 2. So I subbed x is equal to 2 over here, and I will get negative 2 over 27. So there's my final answer right there. Okay, so that's essentially it for higher order derivatives. It's really just a matter of taking the derivative of the derivative, and you keep going if you have to even go further higher order. Okay, thanks for watching.